We are going to kind of get a jump start on second semester. So I want to just kind of introduce some of what we're going to be doing in second semester. So if you think about first semester, we pretty much took derivatives the entire semester and then dealt with applications. You know, what do they mean? What can we do with them? Things like that. So second semester, we're kind of focusing on working backwards, and we're looking at antiderivatives. So I have a page basically of functions, and we're going to first just kind of refresh and do a simple derivative on each function. So first one, I have a polynomial. When I take the derivative, I'm going to power rule it. So I get 6x squared minus 8x plus 1, and the derivative of a constant is 0. So keep in mind, when I'm taking a derivative, I bring my exponent down to the front and multiply. Then I lower my exponent by 1. Bring the exponent down to the front and multiply. Lower the exponent by 1. Okay? That's a simple power rule derivative. The next one is a simple trig derivative. So the derivative of sine of x is simply cosine of x, and the derivative of a constant is 0. Tangent, another simple derivative. The derivative is secant squared x plus the derivative of a constant is 0. 1 over x. I could also write this as x to the negative 1 power. So I'm going to power rule it. Negative 1, x to the negative 2. Next one, the derivative of e to the x is simply e to the x plus the derivative of a constant is 0. And the derivative of natural log of x is 1 over x. Okay, notice that in all these simple derivatives that I did, I never used product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation. They were very simple derivatives. Now, what I'm going to have you do is I'm going to go back and let's pretend that we don't know the original function. Let's see if we can work on figuring out what the original function would have been. This is called an antiderivative. So I'm looking at the derivative of something. What was the original function? So, first term, you have to think, what did I take a derivative of in order to get 6x squared? So to undo the power rule, here's what we're going to do. We are going to raise our exponent by 1, then divide the coefficient by it. Right? So I'm going to raise it to 3, then divide. This one, I'm going to raise it to 2, then divide. Raise it and divide. This one, I think, just had an x on it. And then I don't know what the constant was. I mean, I do know what the constant was, but if I hadn't just done a derivative, I wouldn't know what that constant was at the end. And when we do a general antiderivative like this, we're not going to know. So we just have to go plus, and we usually call it a capital C for constant. There was some constant hanging off at the end of our function. It could have been 0, or it could have been negative 15. All right, next one. What has a derivative of cosine? Well, that's sine. What was the constant? I don't know. So the antiderivative of cosine is sine. What's the antiderivative of secant squared? Well, what function has a derivative of secant squared? Oh, that's tangent. What was my constant? I don't know. So a quick rewrite here allows me to power rule backwards to do my antiderivative. So I'm going to raise it by 1, then divide. What was my constant? I don't know. What function has a derivative of e to the x? E to the x. Don't know what the constant was. Okay, so you can see that they match up perfectly. The only difference is going to be this one, and I'll try to explain why here in just a minute. So what function has a derivative of 1 over x? Well, that would be natural log of x. And then there was some constant hanging off at the end. Now, here's the only difference. Here's the only time where you can see how my antiderivative completely matches up with the original, of course, except for the constant that we couldn't figure out. Matches up perfectly, matches up, matches up, matches up. This one's the only one that's not going to match up perfectly. So when you start with log of x, natural log of x, and you do a derivative on it, this is what you get. When you work backwards, when you go from here to here, we have some domain issues. So the antiderivative of 1 over x is going to be the natural log of the absolute value of x. Let me see if I can explain why here real quick. When you have a function, its domain carries over into its derivative. So, domain is all real numbers. Carry it over into its derivative. The domain is all real numbers. Now, there can be times when you do a derivative and your function was fine at some number, but your derivative blows up. So that happens occasionally where we go from here to here, and now all of a sudden I have to exclude some out of my domain because there's something that makes the derivative blow up that didn't make the original blow up, right? This could be continuous somewhere, but then non-differentiable. Okay, and then also from here to here, this domain is all real numbers. Let's do an antiderivative on it. My domain is all real numbers. So when we're doing this type of problem, your domain carries through. When we're doing this type of problem, your domain carries through. When we're starting here and trying to come up with the original or its antiderivative, our domain carries over. My derivative of sine carries over. My domain for my sine function, all real numbers, carries over to cosine. If I'm doing an antiderivative, so let's say we didn't start here. Let's say we're starting here and we're figuring out an antiderivative. My domain for y prime carries over to y. All the numbers that were valid here are going to be valid here. And it works, and it works, and it works until we get to natural log of x. So let me talk about domain first. First semester, when we go from a function to its derivative, the domain for natural log of x this is the graph of this. So my domain is, let's see, what x's does this contain? Positives. We can't include 0. We can't include negatives. So my domain is all positives. When I look at this, as a result of doing a derivative on this, I really only have the positives. Think about this. Do a toothpick test on natural log of x. So way over here, look at my toothpick. My slope is positive and super big. Still positive, still positive, still positive, not as big, Not as big, not as big, not as big, closer, 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 closer to 0. So if we look at slopes on this, this is what the picture looks like. Huge positives, decreasing, 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 approaching 0. This, as a result of this, produces this graph. Now, second semester. Ready? Let's start here. Let's start here and do an antiderivative on it. So this is my starting place. Ready? Let's look at the domain of 1 over x. Domain for 1 over x is, well, the graph looks like this. Okay? Again, I'm not looking at this as a result of a derivative. I'm just looking at this as its own little function. So the domain of 1 over x is everything but 0. Now, if we start with this domain, ready? Carry it through. Carry through all numbers except 0. How does that look over here? Well, if I didn't have the absolute value signs, I would have a problem. You can't ln a negative. You can't natural log a negative number. Well, shoot, what am I going to do? Because I just carried all these negative x's over from my domain. How am I going to fix that? I carried all these negatives over and now all of a sudden they don't work. That's why you have to put absolute values around the x when you're doing an antiderivative of 1 over x. Okay, so it's kind of all about what type of problem are we doing, what are we starting with, what are we ending with, and how does my domain carry through. Anyway, this is the only one whose antiderivative doesn't like perfectly match up with its original equation. Alrighty, now real quick, let's talk about notation because you're going to be, now second semester, you're not just doing antiderivatives. You're still doing derivatives. You know, so sometimes you'll have to do this type of problem. Many times you'll have to do from here to here, this type of problem. So let me make sure you're okay on how to label your derivatives and your antiderivatives because you know I place a huge importance on labeling your work. So, and I've got the original or an antiderivative on top and the derivative on the bottom. This is how they match up and this is how they go together. If the original is called y, we often write y prime for its derivative. When you're, okay, so second semester, a lot of what you're going to be doing, you're going to be starting here. Hey, this is given to you. Find this. So you need to know what to call it. So if you're given a y prime and you're doing an antiderivative on it, you're going to call it straight up y. If you're given f prime and you need to do an antiderivative on it, you're going to call it f. And keep the cases the same in this case. So if this is little f prime, this is little f, okay? If you're given little f and you're asked to do an antiderivative, at this point you'd be like, I don't know what to call it. So if you're given little f, you're going to call its antiderivative big F. Thus, when you're given big F and asked to do a derivative on it, you all, up to this point, you all have called it big F prime. You can still call it big F prime, or when you do a derivative on it, you can call it little f. It's up to you. And same for any variable. If you're given a g of x function and you're asked to do an antiderivative on it, you're going to call it big G. Likewise, if you're going to look at big G and you're going to do a derivative on it. This is what you've been doing up till now. This is acceptable also. Okay, let's get through some examples here. We're going to find the most general antiderivative of each function. So this one is called little f. I'm going to do an antiderivative on it. I'm going to call it big F. Now, I'm going to think, okay, what function could I have done a derivative on and gotten sine of x? Well, I think it's cosine of x. Let me see. Cosine x, don't forget plus the constant. Quick check. Is the derivative of cosine sine? Oh, wait, no. The derivative of cosine is negative sine. So this one had to have been a negative. Negative 1 times the derivative of cosine is positive sine. Next one, I'm going to call it big F. Watch what happens if I tried to like unpower rule this. What happens if I raise it and divide? Not happening. It's okay. You know we have the special antiderivative for that. It's going to be natural log, of the absolute value of x plus some constant. Okay, and this one, x is my variable, n is some constant, but not negative 1. So it's not this type of problem. It's any exponent besides negative 1. So I'm going to, kind of like unpower rule it. So I'm going to call it big F, raise it, and divide. Now, when I said, so you remember you raise it first, then you divide by whatever you get. I could have, instead of writing it like this, I could have out in the front written 1 over x plus n, or 1 over n plus 1. It's whatever. Okay. This one's worded a little weird. Find all functions, okay? Such that this is the derivative. All right, so I'm going to do an antiderivative basically on each term, but before I do a derivative on this term, I did a quick rewrite to simplify. I always want to simplify before doing a derivative or antiderivative. So since this is little g prime, I'm doing an antiderivative and I'm going to call it just g. You all know that when doing a derivative, when doing a derivative, you keep the constant there and then do the derivative on that. So constant stays there. I think that cosine has a derivative of, it's almost so close. There we go. Cosine has a derivative of negative sine. So the 4 stays there. It's the constant out in front. The negative has to be there. So when I check it and I do a derivative on that, negative times a negative is a positive. Plus. Next term, I'm going to raise it and divide. Plus a constant. And it said find all functions. Kind of weird, but all functions mean there are infinite possibilities for C here, for my constant. So this means that there are basically an infinite number of solutions for the antiderivative. Alrighty, there you go. Power rule. Remember, you're going to raise it first, then divide. That's kind of how you undo the power rule. All right, guys, good luck.